Hello everyone, myself Monica. Today I am going to explain about logic operations and curved surfaces. In computer graphics using OpenGL, logic operations can be performed using the blending functionality provided by the OpenGL pipeline. Blending allows you to combine the colors of pixels in the frame buffer with incoming pixel colors based on criteria blending equations. The blending equations can incorporate logical operations to achieve different effects. Here are some common logic operations in computer graphics using OpenGL. Logical AND. To perform a logical AND operation, you can use the following blending equation. That is, this equation takes the source color, that is incoming pixel color, and the destination color, that is existing color in the frame buffer. It performs a logical AND operation on their alpha components and then blends the color using the specified factors. Logical OR. To perform a logical OR operation, you can use the following blending equation. That is, this equation takes the source color and the destination color, performs a logical OR operation on their alpha components, and then blends the colors using the specified factors. Logical XOR. OpenGL does not provide a built-in or blending equation for logical XOR. However, you can achieve the XOR effect by using custom fragment shaders, which allows you to write your own blending equations and operations. Logical NOT. To perform a logical NOT operation, you can use the following blending equation. That is, this equation takes the source color and the inverted destination color, that is by subtracting the destination color from the white, and then blends the colors using the specified factors. These are just a few examples of logical operations that can be performed in computer graphics using OpenGL. The blending equations can be customized further to achieve different effects and combination based on your specific requirements. In computer graphics using OpenGL, curved surfaces can be represented and rendered using various techniques. Here are a few commonly used methods for creating and rendering curved surfaces. First one is polygon meshes. Curved surfaces can be approximated by using polygonal meshes composed of triangles or quadrilaterals. This technique involves dividing the curved surface into smaller planar polygons and rendering them individually. To create a smooth appearance, the polygons can be subdivided further or the mesh can be redefined with more vertices. This approach is often used for real-time rendering and curved surfaces. Bezier and B-spline curves or surfaces. Bezier and B-spline curves and surfaces are mathematical representations that allow for precise control over the shape of curves and surfaces. These curves or surfaces are defined by control points and interpolation rules. OpenGL provides functions like glmap1 and glmap2 to specify control points and generate curve or surface geometry. Non-uniform rational B-spline. These surfaces are an extension of B-spline surfaces that incorporate weights. These allow for more flexible control over the shape and provides smoothness at the joints between curves or surfaces. OpenGL supports non-uniform rational B-spline surfaces through the GL-NURB surface functions. Subdivision surfaces. Subdivision surfaces offer a method to represent and render curved surfaces based on recursive subdivision and refinement of control meshes. The control mesh is divided into smaller polygons and subdivision rules are applied to generate more refined surfaces. This technique provides smoothness and detailed control. Although OpenGL doesn't have built-in support for subdivision surfaces, various libraries and techniques are available for implementing them. Implicit surfaces. These surfaces define a surface based on a mathematical equation or function. The equation describes a field and the surface is extracted based on certain criteria. Techniques like marching cubes or raycasting can be used to render these surfaces. Although OpenGL does not provide direct support for implicit surfaces, you can use shaders and GPU programming to implement custom rendering algorithms. It's important to note that while OpenGL provides the necessary functions and tools for rendering curved surfaces, the actual implementation and control over the visual appearance often require additional mathematics algorithms and programming techniques. Here is an example for curved surfaces. Code Code uses the GLUT library for windowing and event handling. It defines a 4 into 4 array of control points that define a Bezier surface. Here first, the necessary header files are included. That is hashtag include glut.h for OpenGL and glut functionality. And the control points for the Bezier surfaces are defined in a 4 into 4 into 3 array called control points. Each control point has three coordinates, that is x, y, z, and represent a point in 3D space. The draw Bezier surface function is defined inside this function. The glmap2f function, this is called to specify the control points for the Bezier surface using the control points. This GL map to vertex 3 specifies that each control point has three coordinates, and GL vertex 3 call enables the use of the specified control points. This GLmap grid 2f is then used to generate a grid of points on the surface. The parameters defines the number of subdivisions in the u and v directions. Finally, the GL eval mesh 2, this function is called to evaluate and render the surface using the specified grid. This GL fill specifies the surface should be filled. This display function is a display callback function which is called whenever the windows needs to be redrawn. It clears the color and depth buffers using GL clear, sets up the view using GL load identity and GL lookat. Reshape function is a reshape callback function which is called whenever the window is resized. It sets the viewport and adjusts the projection matrix using GL viewport and GL perspective. In the main function, glut initialization is performed using glut init. The display mode is set to enable double buffering, RGB color mode, and depth buffer. The window size is set using glut init window size, and the window is created with glut create window. OpenGL states are set with GL enable to enable depth testing and GL clear to set the clear color. Callback functions, that is display and reshape, are registered with glut using glut display function and glut reshape function. And the main event loop is started with glut main loop, which handles events and continuously updates the display. This code sets up a basic OpenGL program that displays a Bezier surface defined by control points. When executed, it will open a window and render the curved surface. You can modify the control points or the parameters in the glue perspective call to experiment with different shapes and perspectives. Thank you.